live on YouTube. So I know everybody's well behaved, but I have to point that out. It's just setting up the stream now. Live on YouTube. Okay. Okay, thank you very much for joining yet another Cycle25 talk. Today, I am super lucky to have Alan, W2AEW. I didn't even bust his call today. Mr. Scope. This came out of a conversation that I have to thank a few people for helping enable. Pat's one of them, but basically what I was looking at was, boy, it's entirely selfish for me. I have a scope. I don't use it to its full capability. I barely understand it. Boy, and then I tripped over this wonderful deck that Alan had done some years ago on scopes for dopes. So explaining basics for oscilloscopes, how to use them in the Hamshack, what are the basics around that, what do you need to know to get started. And so then I approached him and said, hey, could you update that for us and come talk to us? So he was silly enough to say yes. And with that, Alan, I will turn it over to you.
All righty. Well, anyway, good morning. And I see my friend Pat in here sitting in front of a wiggly square wave. Need a shorter ground.
We got to fix that.
Yeah, we got to talk about that on about like okay. 37. So we'll get to that. But let me do a quick share of my presentation for us here. And let's see, make sure you all can see that.
I got it.
All righty. So the original version of this talk that I did was probably more than 10 years ago. Didn't include any of the digital stuff, and it was done for the New Jersey Antique Radio Club at one of their meetings on what used to be part of Fort Monmouth. It was actually an area called Evans area, or Camp Evans. And it's where the U.S. Army Signal Corps during World War II did a lot of their radar research. And one of the guys that worked there prior to founding Tektronix is Howard Vollum. So it was just kind of interesting that we were doing a scope talk in a place where one of the founding members of Tektronix actually worked before Tektronix existed. So kind of cool. So we're going to call this basics of oscilloscopes in the Hamshack, or oscilloscopes, and then the use in the Hamshack here. So we'll just kind of get rolling. All right, so here's our agenda. We're going to talk a bit about analog scopes first, because that's what many of us have, because you can almost get them for free these days because people want the digital stuff. We'll talk about all the various controls and what they do. Ryan, you mentioned that you've got a scope and you don't use it to its full potential. I'll tell you the truth is that most people will use about 10 or 20% of what their scope can do, especially today with the digital scopes with all the different features. So don't feel like you're not, as long as you're using it for the applications that fit for your Hamshack use and things like that, great. So don't worry about, you might not ever need the delayed dual time base or something like that, but don't worry about it.
Okay. Alan, would you like questions as we go, or do you want to hold those to the end?
Oh, I'm fine taking them as we go. It's just if we do them in the chat, I won't see them. So
okay. So what I'll ask is people just stay muted for most of it. That'll keep side conversations from getting silly. Yeah. But come off mute and just call out the question from time to time.
Or if you've got a question that you don't mind waiting to the end, throw it in the chat and we'll deal with those at the end. But if there's something that I got to talk, on a slide that something wasn't clear, you have a question, just give me a holler. So we'll talk about the basics of digital scopes, some of the differences in terms of how they operate, that type of thing. We'll talk about probes, and we'll talk about some examples of how you can use a scope in your Hamshack. So the cathode ray oscilloscope, which is the old analog scopes, I've just kind of got a pictorial picture here of the scope, or the tube itself, the CRT. And essentially, it's kind of like a TV tube in the sense that you've got an electron gun firing an electron beam at the phosphor on the screen that glows as the beam is kind of swept through. That beam is directed to go across and up and down based on horizontal and vertical deflection plates. And those horizontal and vertical deflection plates are driven by amplifiers that get input signals, to drive the beam back and forth through the horizontal circuit, and then also to drive them vertically through your input and then the vertical amplifiers in there. So this is really a very basic block diagram of an analog scope. You can think of it as really just a live graphical voltmeter. It's really all it does. It displays essentially voltage variations over time. And that's the simplest way to think about what a cathode ray oscilloscope or any oscilloscope is. The screen is typically broken up with gradicules. And when we talk about things like volts per division or time per division, we're talking about these kind of major divisions. And it's typically a 10 by 10 or a 10 by 8 array of divisions on the scope. So those major divisions are the ones that we're referring to when we say volts per division or microseconds per division or something like that. And some of the other, there's some other additional markings that can help with things like making rise and fall time measurements. And then each of the major divisions are typically broken up with 5 dashes for minor divisions to help you to make some estimations of voltage and things like that beyond just the major divisions. So the display system, typically its controls are those that are things like beam finder, trace rotation, focus, and intensity. And depending on the scope, they'll look a little bit different. There are some controls that we use more often, like the trace intensity or maybe the focus you might use more often. Something like a trace rotation, you don't use that often. Trace rotation refers to any tilt that there might be on the trace when there's no input. Ideally, it's going to be exactly parallel to the horizontal grid lines or radicule lines. But because it's a magnetic deflection system, depending on the magnetic field in your lab or where you're on your bench and where you put the scope, you might get a little tilt on the display. And this allows you to compensate for that. Some of the real older scopes actually with the round CRTs didn't have a trace rotation. You literally would loosen up the clamps holding the CRT and you'd turn it to align it up. But they'll look different on different scopes. This is just another view of what it might look like. And then there's one called beam finder. The beam finder, what it does is it collapses the deflection voltages for the horizontal and vertical down to the point where, let's say you turn your scope on, you're probing on your signal, and there's nothing on the screen. Well, why is there nothing on the screen? Is there nothing on the screen because you're not triggering right? Or is there nothing on the screen because the horizontal and vertical adjustments aren't set right, and if the trace is way off the top or bottom or left or right of the screen? Hitting the beam find will kind of collapse all those voltages so you can kind of see where it is. Oh, it's way off to the left. I need to adjust my horizontal position to the right to kind of get it on, something like that. But that's what the beam find is, just a momentary push button to kind of bring the trace, if there is one, onto the screen somewhere so you can see which end it was thrown off the side of. So the vertical system, this is the system that processes all the inputs that you put into the scope, the signals you want to measure. And it also is typically what will define the bandwidth of the scope, right? The bandwidth of the scope is, think of the front end of the scope as a low pass filter, right? It's going to pass signals from DC and then it's going to roll off at some point, okay? Like a low pass filter. That roll off point, that 3 dB point, is called the bandwidth of the scope. And it's typically going to be dominated by the preamp and amplifier that are inside the scope driving those vertical deflection plates. But then there's other controls to control the position and coupling and sensitivity of the signal that gets applied to those vertical deflection plates to move the beam up or down. Okay. So those controls, again, I've got a number up here to show what they look like. Typically, in most scopes these days that you'll have some calibrated vertical scales. And it says, you can see it says volts per division here. This one says volts per division, ranging from 2 millivolts a division in this case up to 5 volts a division over here. This one's 5 millivolts to 20 volts a division going around. Some of the older service scopes that you might find, and I would say steer away from, are these uncalibrated scopes where you basically just have an adjustable vertical attenuator and a vernier control. They're good for looking at relative amplitude waveforms and things like that, and you could put a known amplitude into it and adjust things to kind of get a calibrated thing. But these days there's almost no reason to use those because you can get good calibrated vertical scales on scopes pretty easily these days. Okay, so it's often called the vertical attenuator control because if we go back to the previous slide, you'll notice that we really have an attenuator ahead of a preamp. Okay, so when we adjust that vertical scale, we're not adjusting the gain of an amplifier. Okay, we're adjusting the magnitude of a signal going into a preamp. And the reason for that is much like if we think about a receiver design or a transmitter design, when you tune your receiver, you're not adjusting a tuned circuit, to dial in a particular frequency that you want to measure. You're basically dialing a local oscillator and a mix and a conversion stage to put the signal of interest you want into an IF stage that does all the filtering and processing, because it's a lot easier to do all of the filtering and all that stuff on a fixed frequency. Okay, so this is kind of similar to that. It's a lot easier to set up and design the front end of a scope with a fixed amount of gain, so you can get the transient response, the frequency response, the linearity, performance of that, all set up with a fixed gain, and then you just adjust the amplitude going into it. Okay, so that's a lot easier to do than to have a variable gain amplifier that maintains its bandwidth and flatness across a wide amplitude range. So that's why it's often called an attenuator control. Okay. One thing I'll make a note of here is you'll notice one of the controls that you have, so it says down here, AC or DC coupling. You see AC or DC coupling over here, AC or DC coupling. This is not like a DMM, right? Whereas a DMM, you select DC to measure DC voltages, you select AC to measure AC voltages. That's not the same thing here. AC or DC coupling basically determines whether or not we essentially have a capacitor in series with the input or not. And so what that allows us to do is, let's say I'm looking at ripple on top of a power supply voltage. So let's say if I had ground, it was here, and then this was where my power supply voltage was, and I could see the ripple on it. If I wanted to zoom in on that, right, I could go to a lower number of volts per division to get more sensitivity, but then I might have to adjust my position to bring the signal back down on the screen, right? Because if this is say 5 volts, or say 2 volts a division right now, right? 1, 2, 3, 4, and that's 5 volts. If I set it to 2 volts a division, this signal will go right up past the top of the screen. So I have to bring my vertical position down to bring it back onto the screen again. Now, eventually you'll run out of vertical position adjustment. Okay, so what AC coupling allows you to do is throw a series capacitor in that input path, get rid of the DC component, okay, and then you can adjust the volts per division however you want. So now you're just focusing on the AC wiggle, if you will, the ripple that's on top of the power supply. So it's funny that oftentimes if you're looking at DC signals, looking for ripple, you often will use AC coupling. Okay, so a little counterintuitive, but that's really what you would often do. Conversely, let's say you're working on maybe like an audio amplifier, okay, and you're getting a little bit of clipping or something, a little bit of distortion. If you're probing around in that circuit, it might be helpful to know why is it clipping? Am I clipping because the signal is being driven into the rail, or am I clipping because I'm driving, a voltage down and saturating a transistor or something like that? So in that case, it's helpful to not only see the AC signal, but where it is in a DC standpoint. So looking at those AC audio signals through an amplifier, you might want DC coupling to understand both the bias and the AC wiggle on it. So the coupling control, again, not like a DMM, it really controls how the signal gets processed through the scope, whether you want to focus on just the wiggle and ignore and reject the DC component, or you actually want to include the DC component in what you're measuring. So the last thing I'll mention too is that notice on the front panel of the scope, you will see notations like this for the input impedance of the scope. Most of the scopes, or most all of them, will essentially be 1 megohm in parallel with some amount of capacitance. This is 1 meg in parallel with 15 puff, and there's some down here. There's another one down here. This is 1 meg and 25 puff. And then some higher speed scopes will often have the option to switch in a 50 ohm termination for doing some RF work. But that's typically only for scopes that are 500 megahertz bandwidth and above. Okay, most of the time it's going to be 1 megohm. Okay, but the capacitance is important to note, and we'll discuss this a little bit later when we talk about probes. So, but that is printed typically on the front panel of your scope. All right, any questions here? Everybody's awake? Okay, no snoring, that's good. Okay. So more on vertical, let's talk about vertical modes. Okay, and these are some of the examples of the different ways vertical modes might appear. There might be push buttons, there might be an actual vertical mode switch. And here I can see right above the vertical controls, I see the vertical mode controls. Oh, one more thing I should mention, and I'll talk about it right here. typically on the volts per division, you'll see a center concentric knob, and you see it says cal with a counter or clockwise turning arrow. What this does is if you turn that cal knob all the way to the right, it'll click. And when it's in that clicked position, now you're in that calibrated number of volts per division. You do have the option of turning it to the left and doing a kind of a vernier adjustment. So if you wanted to make the waveform on the screen a given size, like maximize it on the screen, you didn't really care about the actual volts per division, you could use the variable for that. And it also can be used for doing things like some rise time measurements and all, but most of the time you're going to leave this thing fully clockwise in its clicked detented position to get the calibrated volts per division. Okay, so meant to mention that on the previous slide. So in terms of vertical modes, right, you can select to view, depending on how many channels you have, channel 1 through channel 4, you can select one channel or the other. You can select Alt. What Alt does is when the beam sweeps across, it'll first sweep across showing you channel 1, the next sweep will show the channel 2, the next sweep will show channel 1, it'll alternate back and forth. But oftentimes at your sweep speeds are fast enough that you don't see this, okay? You just see 2 live traces on the screen, and they're both on the screen because the persistence and the phosphor is gonna leave them on there. So it just looks like they're there. There are instances, though, where if you're looking at relatively low sweep speeds, like you're going along at 100 milliseconds, 100 milliseconds per division, which would give you 1 second could go across the screen, you'd actually see it alternate between channel 1 and channel 2. And if you wanted to look at both of those signals at the same time, the Alt mode really doesn't help you. And that's where you'd want to use something called the chop mode. What chop does is that relatively quickly, tens of kilohertz, will bounce back and forth between coupling to channel 1 and coupling to channel 2, but you don't see that. Okay, what you'll see is essentially two beams. Looks like 2 beams going across the screen. It's really one that's going back and forth with a blanking in between, so you don't see it. So chop is like Alt for when you're looking at using lower sweep speeds on your scope. Alt is what you'd use for higher sweep speeds where you won't have any flicker between the going back and forth between multiple channels. But both of these apply only when you're looking at more than one channel at a time simultaneously. You'll also notice that there's an add mode where I can add 2 channels together. Well, why would I want to do that? Well, hang on a sec. There's also an invert mode where I can invert 1 channel. Now the add kind of makes sense. Now I can actually do an add and invert and actually do the difference measurement, maybe across a component. Because unlike a DMM, where you take the leads from a DMM and you can poke them anywhere you want on the circuit, right? I want to look at the voltage across this resistor. I want to look at the voltage across that, the base to emitter or that transistor or something like that. You can just willy-nilly poke that wherever you want. You can't do that with a scope probe, right? Because a scope probe, one end of it is always ground. It's tied to chassis ground. So I can't make a differential measurement across 2 arbitrary points, right? I'm always making measurements with respect to ground. So in order to make a measurement across a component, I would actually use 2 probes, both with respect to ground, and do an add and invert. So it's essentially taking channel 1 minus channel 2, which is basically like using a DMM across it. So that's a kind of the easy way to make a differential measurement across a component by using the add and invert. And that's why it's typically on all these analog channels or more. Yeah.
So I think it's interesting to point out for people that haven't used scopes, that's really something to be aware of, that you don't want to go poking your ground lead trying to make a differential measurement. You'll short something out. You'll short something to ground potentially, and that's a terrible problem to have when you're trying to troubleshoot.
Oh yeah, you'll let the smoke out. That's for sure. So that's a good point, Pat. And it is something that we'll talk a little bit about later too. But there are a couple of scopes, and not many, that have isolated channels where you can actually poke the probe, the probe lead and its ground lead anywhere you want. But 99% of the cases, the ground lead on the scope is connected to chassis ground. If you're working on a battery operated circuit, then you can kind of get away with it because then you don't have any other ground connection. But if you're working on anything that's plugged into the wall or a power supply, you do have to kind of worry where ground is, and always make sure you only connect the scope probe's ground lead to ground in your circuit. Okay. So the horizontal system controls, the sweeping of the beam across the screen. Okay. And there's a bunch of little pieces to it here. But in a sense, there's a sweep generator, which generates a voltage that is applied to the deflection plates to move the beam back and forth. And that's very quickly swept back to the other side and does it again. And there's a number of controls here we'll talk about in terms of how we actually control that. On the analog scopes, we call it a sweep time control or a time-based control. On the modern digital scopes, unfortunately, they call it horizontal scale. Okay, because there is no sweeping in a digital scope because we're basically just digitizing signals. But I still call it sweep time or time base because that's really where it comes from, is basically creating as a ramp voltage that goes across. So let's take a look at this. There's actually a couple of variations here that I want to talk about. So the old service scopes that I mentioned earlier that didn't have the calibrated vertical, they also don't have a calibrated horizontal, and these were called recurrent sweep scopes. So anytime you see an old scope that for the horizontal has a frequency range like 10 hertz, 100 hertz, kilohertz, 10 kilocycles is a dead giveaway that it's kilocycles, and a vernier control like this, this means that the horizontal is driven by essentially a free running sawtooth wave. So it runs continuously, it's free running. There's a sync control that can be used to kind of try to injection lock a piece of your input signal onto this sawtooth to try to keep things somewhat synchronized, but they're not calibrated. It's really older and really much simpler technology. And again, today, almost no excuse to be using this anymore. Just if you're looking for a scope at a Hamfest and it's got these types of controls, it's a recurrent sweep scope and just not going to be as useful for you as a triggered sweep scope, which is what we're looking at here. A triggered sweep scope, the sweep essentially runs across the screen. This voltage represents essentially a position across the screen horizontally, and then it resets, and then it waits until it gets triggered again, and then it sweeps again. So much, much better technology in terms of control, getting a nice stable waveform to look at on the screen, and the sweep time is calibrated in milliseconds or microseconds or nanoseconds or seconds per division. Okay, you don't have any of that really with the recurrent sweep scope. So again, because even these trigger sweep scopes have been around since the 60s, there's really no excuse for using a recurrent sweep scope and getting limited by that anymore. Okay. So let's talk about triggering. Again, on the recurrent sweep scopes, it's called sync. Why do we want to trigger or synchronize? We want to stabilize that waveform on the screen. And what that does is you're trying to lock the sweep to some feature on a repetitive waveform. Okay, so that we always start the sweep at the same point. So as you get multiple sweeps, the waveform overlays on top of each other, and you get a nice stable waveform to look at, like the background on the background behind Pat there. Okay, so again, with the old recurrent sweep scopes, there was a sync control, and what that would do is take a portion of the input signal and inject it into that horizontal oscillator to try to injection lock it, and that's the only control you had. It's just horrible. Okay. So, and this is kind of what it looked like. You select an internal sync source, and the sync amplitude controlled how much of the input signal you'd inject into that oscillator. And you'd have to mess around with the horizontal oscillator vernier and this control to get a stable waveform. It's just horrible. Don't bother. Don't use those. Okay. Use a triggered sweep scope. Okay. The trigger sweep scope, again, the sweep starts when the input signal meets a trigger criteria that we'll talk about here in a minute. And it's, again, a whole lot more powerful and much, much, much easier to get a stable waveform on the screen for you to look at. Okay, so let's talk a little bit about the trigger controls. One little neat trick that I'll give to you is that on most older Tektronix analog scopes, and a lot of other manufacturers kind of followed suit, sometimes the triggering thing is the thing that can get most people kind of hosed up. How to set it up, I don't know what to do or whatever. And the secret is, if there's a set of controls like these lever controls here, bring them all to the top. Normal trigger mode, positive sweep, auto trigger, DC couple, auto triggered, and internal trigger mode. Throw all those trigger buttons up to the top, and you'll most likely get a trace you can start working with. It's just kind of a little trick. It's almost universally true. So let's talk about triggering. So again, triggering is going to pick off signals from the vertical input, because we want to look at our input that we're sending into the scope and basically lock on a portion of that and then send off the sweep to start at that location on our waveform. So you typically can get signals from the input or an external, a separate input to trigger. We can talk about coupling and the sources. And that's going to basically provide an input like the trigger on a gun to kick off the horizontal sweep. The trigger source is typically internal, which means that I'm going to pick off a portion of I'm going to use my input signal as my reference of what I want to trigger on. That's 99% of the time, that's what you're doing. You might have another signal source you want to trigger from. So you want to look at waveforms with respect to some other signal, and that could be an external trigger source. In some cases, if you're looking at doing things that are related to the line frequency or power supply, AC line frequency, like you're looking for ripple or something like that that's synchronous to the AC line, you can simply do a line trigger. And it's also a way of just getting a nice, good, consistent trigger. If you just want to get a nice waveform that's updating all the time, but you don't want to have mess around, try to trigger on just the signal itself because it doesn't matter. A line trigger is a nice, handy way to do that. Okay, so that's our source selections. The trigger mode, we'll talk about auto here in a moment, but there's auto trigger mode, there's normal trigger mode, which basically says, I'm going to get a sweep when I get a trigger. That's what you're using most of the time. You might actually use auto most of the time, but again, we're going to talk about that in a minute. A single trigger would just give you a single trace in response to a trigger and stop. Now, for an old analog scope, that's not terribly useful unless you got a scope camera there to kind of capture what that trace is, but it's there. And also a lot of the older scopes have a TV trigger mode that allows you to trigger on like the NTSC composite video signal to look at either horizontal lines or vertical sync pulses and trigger on those. And then similar to the vertical section and vertical controls, there's also trigger coupling. So you may choose to do, DC reject or AC coupling, of the signal into the trigger. So you're only going to trigger on a portion of the wiggle of the signal. You could do DC coupling, and then sometimes there's some other features to do high frequency reject and things like that, but all that becomes pretty scope dependent. And now the digital scopes will have a lot more trigger choices available for you as well. But most of the time you can use a very simple trigger to get what you want to get. Okay, so again, the trigger really controls when that sweep is going to happen on an analog scope. On a digital scope, it more determines what feature I want to capture into memory to go analyze. So let's talk about auto trigger. Here's a picture of my 465 scope, and there's the auto trigger button right there. It's not necessarily what you think it is. Auto trigger does not automatically set up your trigger settings. That's not what it does. Okay, so it's not like an auto set button, but it does provide a very useful feature. So it's really a usability aid. Because let's say if we didn't have this auto trigger and I'm trying to look at a waveform and I got a blank screen. Why do I have a blank screen? Do I have a blank screen because my adjustments are all out of whack? Or am I not just triggering it right? I don't know. Okay.
Can I just come in on this one?
Sure.
One easy way of explaining that would be to assume that it's an auto free run. In other words, the signal will just free run across the screen. And I think that's probably an easy way to explain it.
That's exactly right. So what happens with auto, and it's exactly as you described, the scope waits for a trigger. If it doesn't get a trigger within about 50 to 100 milliseconds, then it self triggers. It just says, okay, I'm going to issue a trigger anyway. So that kind of is a free run type mode, saying, okay, the trigger you told me to do doesn't exist, so I'm just going to kind of free run here. But if while I'm free running, you actually get the trigger adjustment right, then I'll actually lock on your signal. So what this does is it puts a trace on the scope, even if the trigger event is not satisfied. So you can see what's going on. So you'd say, well, I should be triggered, but I'm not. My waveform is sliding back and forth or something. And that gives you the clue. It's like, okay, the waveform's on the screen. It's I've got the vertical settings right. I might want to play with the horizontal settings, but then I might have to adjust my trigger level to kind of get myself triggered right. But it gives you a way of getting something on the screen, okay? And to give you an aid to figure out how to correct what you might have set up wrong in the trigger. Otherwise, if you have the trigger set up wrong, you'd have a blank screen. So it really is kind of an auto free run. Okay, but it's an auto free run that will switch back to a triggered mode once the trigger condition gets satisfied. Okay, so if your trace is kind of rolling or is unsynchronized, it's likely that you're seeing these auto triggered sweeps and you're not actually triggering on your signal itself. Okay. So the most basic controls and the most common ones are just doing what's called an edge trigger, okay, where you're triggering on the signal crossing through a threshold voltage that you set up with the trigger level control. So here's 4 examples where this is positive slope. I've got the level turned up to a slightly higher positive voltage. So you can see we're starting the sweep on this sine wave, something above ground, right? Because I turned this positive, and I'm starting the sweep on the positive slope when I go from below that level to above it. If I switch the slope down to negative, I'd start at the same point, but then I'd trigger on the portion of the waveform that's going down through that. And similarly, if I move the trigger level down, say below 0, okay, below ground, now you can see the voltage is starting, or the waveform is starting below the center of the screen, and then the slope determines which way we're going from that. Okay, because this is just a continuously running sine wave. It all depends on where you take the picture of it, right? This helps you determine what portion of the picture you want the waveform to start at. But this is the most common set of controls that you'll use. And oftentimes you're just setting up, positive slope, leave the trigger, the slope, the level in the middle, and that's it. But it depends on what your waveforms look like. You may mess around with that to get what you want. Okay, but 99% of the time, you're probably just going to use a simple edge trigger. Okay. So with that, let's kind of talk a bit about the differences between analog and digital scopes. So before I do that, if there's any other questions on the analog scope features, vertical, horizontal, or trigger, let's cover those now before we jump into digital.
One thing I would like to put forward as a suggestion, that is that when you, for instance, want to look at a signal, let's say you're getting close to the bandwidth or close to the edge of the bandwidth.
Mm-hmm.
If you put a signal and say, let's start at 50 kilohertz as an example, and you fill up the full screen with, you've got 10, you're taking up all 10. Yeah. But when you get to the actual bandwidth frequency to 100 megs, you've reduced the signal will reduce down to approximately 7.2 divisions.
Right.
And I think that's something you need to be aware of, or people need to be aware of.
Yeah, in the old analog scopes, we had what was called the old 5 times rule, because this is kind of like a Gaussian single pole roll off on the old analog scopes. So the bandwidth rating, like I said, is when you're 3 dB down. So you're going to be about 70% of the amplitude. So if I had a 100 megahertz scope, I put a 100 megahertz signal into it, the voltage that I read is not going to read the full voltage. It's going to be attenuated down to about 70% of the true value because of the low pass filter characteristics. And the old rule of thumb was that if you wanted to get within 2% of accuracy of your vertical amplitude for a signal, the scope should have 5 times the bandwidth of the frequency of that signal. Okay, so for a 100 megahertz scope, you're only going to get within 2% of the amplitude of a signal up to 20 megahertz, right? And then below that, above 20 megahertz, the signal amplitude is going to start dropping. It doesn't mean you can't see a signal beyond 100 megahertz or even at 150 megahertz. You'll still be able to see it. It's just going to be lower in amplitude. So you can't believe the amplitude, all right, because of that low pass filter characteristic. So that's a good point, Paul. Thanks.
While we're talking about filters, typically what is the frequency on the AC coupling high pass filter?
That's typically down in the tens of hertz. Okay, for the vertical AC coupling is down in the tens of hertz, so that you could look at a 60 cycle thing with no problem. You wouldn't be able to look at something that's varying at like 2 hertz or 10 hertz or something like that. You only see a little bit of it. So it's typically down in the tens of hertz because it doesn't have to be a huge capacitor because it's looking into a 1 mega ohm input impedance, right? So, but it's typically going to be down in that tens of hertz type of value. Okay. All right. Any more questions on analog before we go? Okay. So let's talk a little bit about analog versus digital. So here's a simple, very simplified block diagram of a digital scope. Now it's the same basic front end, right? We're still going to have input attenuator, input preamps, and things like that. But rather than going off and applying that to a vertical amplifier to drive deflection plates, we're applying that signal into an analog to digital converter, which is basically taking samples of that waveform, okay, and sending those samples off to be processed. The trigger system will be looking at it. In some scopes, the trigger system will be looking at the digital samples. In some cases, the trigger system might be pulling data off of the analog input. It all depends on the scope. Ultimately, all those samples that, those pictures, the samples of the voltages over time are stored into memory and then processed to throw on the display. So, but all of this, we have this concept of sample rate, right? How often are we going to be grabbing and taking a picture of the voltage at that instant in time? So that's called our sample rate. And then our sample interval is really 1 over that sample rate. And typically the sample rate is going to be many, many times more than the bandwidth of the scope, right? We know from Nyquist that it has to be at least 2 times the bandwidth of the scope, but in many cases it's much more than that. Like a typical 100 megahertz scope may have a gigasample per second sample rate, okay? So how do we deal with all those samples? So the sample rate, the memory depth to put those samples in, and the horizontal scale are all interrelated, as you might imagine. If I wanted to look at this sine wave, right? If I sample it 10 times, then I need 10 samples of memory. But if I sample it 100 times, now I need 100 samples of memory. If I want to sample this 10,000 times, then I need memory to store 10,000 samples. Okay, so you can see that the sample rate and the acquisition length in time really determine how much memory we have to store these waveform samples. And a lot of the modern, even the inexpensive digital scopes will have mega samples of memory. It's like, well, if I got mega samples of memory, my display doesn't have megapixels of display horizontally. So how do we deal with that? So the acquired samples are then processed into display points. So I might have samples in memory that are much, much tighter in terms of interval than these samples that are going to be used for display. So most scopes will actually take the samples from the waveform memory and then compress them in some way to put them on the display. And in most cases with the modern digital scopes, they'll take all these samples that appear within a display interval, a pixel, if you will, and then maybe cloud them all into a whole column, if you will, of pixels in the display, and then again and again, and then kind of do an intensity grade to kind of emulate what the phosphor did on the old analog scopes to give you kind of an intensity graded display. But there are other display modes that are available, like a peak detect mode, as well as a peak to peak or envelope mode. So there's lots of ways of doing additional processing on those, could be millions of samples, to display them on the maybe 1,000 points that you've got across the screen in terms of the waveform display. So this gives you the ability to get really good resolution on your measurements, but also get good visibility of your waveform as well. So the way the scopes all do this, it's a whole topic for a whole nother talk, but it is something that you'll find, and you almost have to kind of play with the scopes yourself to see, is this going to work for what I want it to do? But in most cases, they're really designed to somewhat emulate what the old analog scopes did. So some digital scopes have got some pretty significant advantages, right? We can capture a waveform and do a single shot on it, zoom in on it, see what's going on. Like here's a stair-step waveform, it's got a little bit of a glitch. We could zoom in on that glitch and see what it looks like. I mean, these are things you can do in some sense if you've got a live waveform on an analog scope with things like a dual delaying time base, but it's really simple to do on a digital scope. You capture the waveform, zoom in, really simple to see what's going on. Also, something that digital scopes give you that is much harder to do on an analog scope is pre-trigger information. Like what happened before my trigger event, right? Well, an analog scope can't do that, right? Remember, because a trigger kicks off the sweep, so you can't see what happened before it. On a digital scope, the scope is sampling all the time. And when you define a trigger, the trigger just says, okay, I'm sampling all the time. When you find this thing, I want to capture the data around that. And I said around that purposely because that trigger position can be anywhere on the screen. So I can look at pre-trigger information or post-trigger information, see what led up to an event and see what happened after it. That kind of thing is a big advantage on digital scopes that analog scopes typically couldn't do. There's often many, many different types of triggers. If you're looking at like digital buses, we can trigger on a bus address or something like that. And of course, there's also automatic measurements, peak-to-peak measurements, voltage measurements, rise and fall time measurements, frequency measurements. These can be made all automatically without you having to count divisions and do things like that. So that's some of the advantages that the digital scope brings you. So more features, oftentimes you can do some waveform math Okay, so I can take one waveform and another waveform. In this particular case, I got a waveform here where I'm measuring the voltage on either side of a resistor in series with the base of a, this was actually an experiment I was doing to look at switching time of a transistor. So this is like the output of the collector. This is these two voltages here, channel 2 and channel 3, where the voltage is on either side of a resistor in series with the base. And then I did a little bit of math to actually do, this voltage minus that one divided by that resistor value to give me a waveform that represented this current. Okay, so these kind of things you can do with a digital scope that you can't do with an analog with doing things like math. Okay, so there's other advanced processing features like a Fourier transform to give you the spectral content of a signal, things like that. Again, features that are in a digital scope that an analog scope doesn't have. Okay, so you would say, well, hey, that's all great. Why don't I just always go with a digital scope? Well, there are some disadvantages to digital scopes as well. One is that they can appear noisy. They're not necessarily more noisy than an analog scope, but an analog scope, the trace on the CRT is drawn by repetitive, sweeps of an electron beam. And it's only those areas that get overwritten with each sweep that light up the brightest. Any little noise disturbances that cause a momentary deviation from where that sweep is going are going to be dimmer. So they don't show up. They're not as prominent. On the digital scope, since you capture and display everything, right, it looks noisier because those things that would be really dim on an analog scope show up sometimes at an equal brightness or a near equal brightness, depending on how the color or the intensity grading is set up. So they can appear noisy, but they're not always. Probably the biggest disadvantage is that digital scopes can alias the waveform. Okay, and this is where the sample rate is not fast enough for the particular waveform. You can say, hey, but Alan, you just told me that 100 megahertz scope samples at a gigasample per second. Well, yeah, it does. But if you are adjusting the horizontal scale down to look at something like 10 milliseconds of division, it's not going to be using the full sample rate when it stores the waveform because you might need megabytes of storage. So it'll cut the sample rate of the stored waveform. It might cut it down to, to something that is too low for your waveform, and you can get aliasing. So here, look, we look at this red sine wave. Let's say that's our normal input signal. But if I was looking at it at a slow time base, okay, or a large, seconds per division type of value, the sample rate might be too low. So if I got these samples at these green points here on the waveform, you can see that I'm not sampling each cycle except but once, right? And if I stitch those points together, which is what the scope will do, it'll show you a waveform that is not your original waveform. And I call this the wagon wheel effect. If you're ever watching the old Westerns on TV and you watch the horse-drawn wagons, and sometimes the wagon wheels look like they're turning backwards, right? It's all because of the frame rate, the 30 frame per second or 60 frame per second of the movie is taking pictures of that wheel when it's in different positions. And it's not taking pictures of it fast enough. It's taking pictures of it, at some sub rate. Those pictures might be at positions where the wheel hasn't completed a rotation. It looks like the wheels are going backwards. That's an aliasing effect. And that's exactly the same thing that can happen in a scope. And this is of particular importance when we start talking about RF applications that we might use a scope for. A good example is, let's say we want to look at the modulated RF envelope, like a station monitor. So I might be transmitting at, on 7.2 megahertz and looking at my single sideband signal, but I want to look at the RF envelope from my voice, from the microphone. Pat, you'd have to dig the microphone out of your drawer. I know you're doing all CW, but so you have to dial down to, maybe a millisecond of division or 500 microseconds of division. And by doing that, the sample rate of the stored waveform may come down where it's going to be lower than the RF carrier, and you're going to alias the signal. Okay, so that's something to kind of be thoughtful of when we're looking at if your application is going to be looking at monitoring your RF envelope. An analog scope is actually better. So oftentimes, if you're looking at your signal and it looks like it's triggered, but you're still getting this wandering waveform, it's not steady. It could be that you're aliasing. Okay. Depending on how you got the scope set up and how much memory you're using, the update rate can be slow, or the responsiveness of the scope can be slow, where an analog scope is instantaneous as you make adjustments and changes. Okay, they can be a bit pricey because it's a newer technology. And they also can generally have, if you ever use XY mode, and we'll talk a little bit about XY mode later, the XY mode on digital scopes is generally pretty lousy compared to analog scopes where it's actually pretty good. Okay. So that's probably all we're going to talk about in terms of, just the digital scopes themselves in terms of features, because the controls are very much the same. You still have the same vertical controls, same coupling controls. Horizontal is just called scale instead of sweep speed, but it's still calibrated in so many volts per division. And the trigger controls are virtually the same, except like I said, there's a lot more triggers available to you, but as hobbyists, we're generally just going to use an edge trigger. So with that, let's talk a bit about probing, which is kind of universal regardless of whether we're talking about an analog or digital scope. Why do we want to use probes? Well, obviously to connect our signal to connect the signal in our circuit to the scope to go look at it, right? And ideally, we want to minimize loading, when we go to measure something, right? The Heisenberg uncertainty principle says that, just the act of observing something will alter it in some way, right? We want to minimize the amount that we're altering the signal, okay? So the probes help us do that. Most probes that we're going to be looking at are passive probes, like 1x and 10x probes we're going to talk about next. But oftentimes there are also active probes like current probes, high voltage probes. There's also RF probes like near field probes and things like that that we might use, or even just a simple wire going into the front of the scope and wrap around your coax. Oftentimes is enough to pick up the RF signal that you're transmitting to look at it. So you can almost call that a probe. It really is just more than a pickup wire. Okay. So let's first talk about the 1x and 10x passive probes. A 1x probe is really just a direct connection to the scope input. All right. And so it's really simple. There's nothing to it. It's just, it just has a nice convenient end on it with a little hook tip, or maybe a little spring-loaded hook like we call a witch's hat, or it's a sharp little probe tip like a probe, and then a ground lead with an alligator clip on it or something. Very simple connection. The problem is that they can have fairly excessive capacitive loading. Because remember, we talked about the scope input. We showed those examples. I've got 15, 20, 25 picofarads of input capacitance. Add on top of that the capacitance from the scope lead itself. So you could be talking about 100, 150 picofarads of loading. And depending on what if you're looking at an audio circuit, you probably don't care. But if you're looking at anything at an IF or an RF signal, 100 picofarads might be significant and might actually affect the operation of your circuit. You're trying to look at the output of a crystal oscillator or something like that. 100 picofarads is certainly going to affect the tune circuit, if you will, of that oscillator. Okay, so that's why most of the time we're actually not going to use 1x probes. We're going to use 10x probes. 10x probes will essentially isolate the probe or the circuit from that cable capacitance and the scope capacitance by putting a 9 megohm resistor right at the probe tip. Okay, so now the circuit is going to see 9 megohms before that capacitance. So the capacitance is now 9 megohms away and is not going to necessarily be as much of an impact on the circuit. Hey, that's good. But now that 9 megohm resistor, eventually is going to form a voltage divider with that 1 megohm input impedance of the scope. So it's a 10x voltage divider. So we're going to reduce our signal amplitude by a factor of 10. Now, in some cases, the scope will automatically detect this, depending on the scope and the probe manufacturer. Sometimes they kind of work together. You plug the probe in, it knows it's a 10x probe, and it adjusts the vertical scale by itself. In other cases, you may have to tell the scope, I'm using a 10x probe, so it adjusts the vertical scale appropriately. Okay, so otherwise your voltage readings will be off by a factor of 10. You won't know why. Okay, the good thing is that it reduces the effect of that capacitive loading on the circuit. The bad is that we have to compensate it. So more on this next. And what does that mean? Okay, but again, most of the time we're going to be using 10x probes. So understanding compensation, it's not a bad thing. You just have to know what it is and do it. So let's talk about probe compensation. So here's a simple model of, say, from here over is the probe. So I've got the probe tip. Okay, I've got the 9 megohm resistor there. I've got a coaxial cable between here and the scope. Okay, the scope has got the 1 megohm input impedance and the parallel capacitance. All right. So if you think about it, if I ignore the capacitors, I've got a 10x voltage divider with the resistors. But this capacitor we can't get rid of, right? So as frequency goes up, at some point, the reactance of this capacitor is going to go down below 1 meg. And now I've got a low pass filter between my 9 megohm resistor and the input capacitance. So that low pass filter will start rolling the bandwidth off. Well, that's no good, right? I'm using this probe to prevent problems with, frequency response by the capacitive loading. So what we do is we actually put a capacitor in parallel with the 9 meg ohm resistor. And what you do is you adjust this capacitor. So now these capacitors have got the same 10-to-1 ratio. In fact, it's the other way around. Instead of 10-to-1 going this way, or 9-to-1 going this way, it's 9-to-1 going the other. But what we're doing is setting up that same ratio. So as the frequency goes up, okay, as the frequency goes up, or at low frequencies, the 10x attenuation is dominated by the resistors. As the frequency gets up past 10 or 20 kilohertz, now the attenuation gets dominated by this capacitive voltage divider between CP, the adjustment capacitor, and the input, the probe's input, the scope's input capacitance. Now, because all scopes don't have the same input capacitance, we have to make this capacitor adjustable. Okay, and the scopes provide you a tool to do that. Right on the front panel of the scope, you'll see a probe calibrator or probe compensation signal on, and it's typically a 1 kilohertz square wave. Now, square wave is nice because at 1 kilohertz, the 1 kilohertz frequency is to the point where the resistor voltage divider is going to work. But because I've got fast edges on it, there's higher frequency content, right? As you know from square waves, you got energy at all of the odd harmonics. So those odd harmonics are higher and higher in frequency, and they'll get affected more by the capacitive voltage divider. So what you do is you hook your scope probe up to that compensation signal, and you adjust that capacitor on the probe to get a perfect looking square wave. If it's not properly adjusted, if it's undercompensated, okay, like if this capacitor was too big, then you'll make the edges slower, okay, and it'll look like this. So you adjust that to properly compensate. If the capacitor is adjusted the other way, you'll be overcompensated, right? And you may overshoot, the signal. That's when this capacitor is actually too big. You'll overshoot the signal. Okay, so you plug into the probe in, and you look at that square wave, and then you simply adjust that compensation adjustment, a little screwdriver adjustment on the probe until the square wave looks good. And what you've done then is given a nice flat frequency response of the probe, so that you can now believe the amplitudes that you see of the signals that are 10 or 20 kilohertz or higher using that probe. Okay, this is something, if you ever, if you look at the probe, sometimes the little adjustment is on the probe itself, the part that you hold in your hand. Sometimes that adjustment is on a compensation box that's attached to the front of the scope where it plugs in. So you just have to look at your particular probe, and it's usually a very tiny little screwdriver adjustment. It's either a hex or like a Phillips or a straight. And you often want to adjust that with a non-conductive screwdriver if you can. Or if all you have is a conductive, you adjust it, pull it out, make sure it's good, and adjust it again. But the good thing is, if you only have one scope, you just have to make adjustments on your probes once and then forget about it. Okay, but the problem is some people forget about it from the get-go and never do it. Okay. So again, most scopes have got that calibration signal for that purpose. Okay, so now this is something I alluded to earlier, looking at the Pat's background picture, is the probe ground. Now, as I mentioned, that's connected to chassis ground on your scope. All right, so whatever point you connect that to, you're going to connect to ground on your circuit. So as long as it is ground, you're okay. If it's not ground, you're going to short that node to ground. So if it's a battery operated circuit, again, may not matter, but if it's not, then you do have to watch where you put that ground lead. But the other thing to worry about is that ground lead is an inductor in essentially the return path. We have this loop, if you will. Okay, so that kind of represents an inductance in the ground path. So that inductance, coupled with the input capacitance of the probe, can create a tank circuit and cause ringing. So you want to keep it short. Okay, if you can. If you're looking at audio signals, things like that, we don't matter. But if you're looking at digital signals that have fast edges, or you're looking at RF signals, we want to keep that as short as possible. So amount of the probes are designed that if you yank this witch's hat off, you'll have a probe tip that looks like this with a little concentric ground ring, like a coaxial, type of rigid coaxial probe. And you can either make your own, or the probes will often come with new that might get lost, a little spring ground clip that you can slip on there. So now I've got a much shorter ground lead. And just as an example, here's a fast rising edge measured with a 5-inch ground lead length, and you can see the ringing on that edge. Okay, that's all due to that ground lead length. that same exact signal probe with this, I've minimized that ringing because I've minimized the inductance in that ground lead length. So again, only you need to worry about it if you're dealing with digital signals, you're probing clocks or data signals and things like that that have high frequency content, or if you're actually looking at RF or IF signals, you might want to really consider how long that ground lead is and how that's going to affect what you're looking at. So let's talk a little bit about XY mode. XY mode is where you might have one channel that actually drives the horizontal position of the beam instead of the horizontal sweep oscillator or the horizontal sweep circuit. You might have one channel that drives that, and another channel that drives the vertical. So this is kind of like the Etch-a-Sketch mode of a scope, right? Where you have the two knobs, you can move the beam anywhere you want based on those two values. This is actually a picture that I think I took a similar picture of this, or I used to do this when I was a kid. I had a scope when I was in high school. I had a scope in my bedroom. I hooked into the back of my stereo, and this is kind of what it looked like when I had the left channel going on to one channel and the right going on to another channel. And listening to Pink Floyd or something like that, you just get this mess. Okay, but you kind of a little bit see kind of anything that's kind of along the diagonal, it was coming out of both speakers, but anything that deviated from that was on the left or the right channel. So it's kind of neat. But it could be used for doing frequency comparison, because if the X and Y are driven with the same signal, you'll get a diagonal line. If there's a phase shift between those signals, that'll turn into an ellipse or a circle or a diagonal going the other way. If there's a frequency difference between them, you'll get like figure 8 patterns or other things like this. These are called Lissajous patterns. I've got a video on that as well. So that's a crude way of making frequency measurements. You could also do things like a curve tracer. There's a very common old circuit called an octopus, which looks similar to this, where I've got a little step down transformer. And I use these two probes to put across a circuit. And I'm essentially measuring the voltage and the current with two probes here, one looking across a resistor, one looking across the device itself. And you essentially can trace out, like a short circuit would look like a vertical bar, an open looks like a horizontal bar, a resistor looks like a sloped line, a capacitor will look like an ellipse. Diodes and junctions will kind of have a wiggle to them, that type of thing. And like, if you ever heard of the old Huntron tracker, it was a little circuit, a little piece of equipment that was used oftentimes in TV service centers, because you might kind of know at particular points in a circuit, if I put this little curve tracer, this Huntron tracker in different nodes, this is what that waveform would look like. And if it deviated from that, you knew something was wrong. Didn't really tell you much about the operation of the circuit, but just told you if things were wrong or not. Okay, but you can build one of these little circuits. It was called an octopus because it had 8 leads when you counted everything that was going out. An octopus circuit, and build a little something like that. And some of the old analog scopes actually have a component tester built in, which is basically that. Okay. Another thing you can do with XY mode, a little more sophisticated, is actually, maybe you do a frequency response sweep. Let's say I had a sweep function generator. Okay, I had the ramp output, the frequency ramp go out to one input. Okay, and then look at, say, the voltage coming out of, say, the IF transformer as I apply this sweep signal into the device I'm testing, and actually look at the frequency response as I go across. So more of a sophisticated use for XY mode if you really like playing with scopes. There's better ways of doing this these days, but this is what XY mode is typically used for. And again, the digital scopes are pretty lousy at XY mode because it's all sampled points as opposed to a continuously moving beam. So XY mode is generally handled much better. Another common way for XY mode, I think I'll talk about later, is looking at like a trapezoid pattern. Like an old station monitor will have a trapezoid pattern to look at things like linearity of your amplifier or something like that. So that's essentially an XY application of the scope. So again, analog or digital. Again, in many cases, digital is better. Automatic measurements, storage into memory, zooming in, etc. But for an RF envelope or things like that, analog is definitely better. Okay, like at slow sweep speeds to see audio, the RF can get undersampled. So here's like a single sideband RF envelope on an analog scope. To me, I get a lot livelier view and a more intuitive view of what's going on with the RF compared to looking at that on a digital scope. Some digital scopes don't have enough intensity grading to make it look like I've got really nice intensity grading here. I can see what's going on. The update rate is going to be instantaneous on an analog scope. It might not update quite as fast on a digital scope. So there's a lot of reasons why for doing RF work, an analog scope is oftentimes much better. So with that, before we jump into scopes in the Hamshack, let's take another quick little break to see if there's any questions on the scopes in particular, and then we'll just talk about a couple of applications where you can use a scope in a shack.
Is it
Now,
worth
this is
mentioning-
Pat. Go ahead, Paul.
Is it worth mentioning anything to do with rise time and bandwidth? The fact that a scope will only handle up to a certain rise time, depending on the bandwidth of the scope.
Yep. Yeah. So the old school figure of merit for that is a factor called 0.35. It's like 0.35 divided by the bandwidth will tell you the rise time of the scope, and vice versa. 0.35 divided by the rise time of the scope tells you the bandwidth of the scope. Okay. And that relationship holds true for most of the analog scopes and most of the lower end digital scopes. It's when you get into the really high end, high speed digital scopes where that factor changes to more like a 0.4 or 0.45 because of the digital signal processing that's going on. Because remember, the faster things move in the time domain, the more bandwidth they occupy in the frequency domain, right? So like a square wave, we said, has got spectral components or frequency components at the fundamental of the square wave and at the odd harmonics. The more odd harmonic components, like the fifth, sixth, the sixth, or the seventh, the ninth, the 11th, the 13th, etc., the higher you go, the faster the edge will be. So again, so if you're looking at I got a 10 megahertz clock that's driving my Arduino or something like that. Well, that 10 megahertz clock might have 2 nanosecond edges. Right? In order to look at those 2 nanosecond edges, I might need a couple of hundred megahertz on my scope in order to accurately see that. Okay, even though the clock signal itself is only 10 meg. Okay, so that's kind of the relationship there. So thanks for that, Paul. Pat, you had something?
I did. Well, first of all, I'd like to say thanks. I've seen this presentation a couple of times, and I've given one like it a couple of times, and I always learn something every time I hear from you. And I really appreciate your YouTube channel. It's been a great learning resource for myself. So I really appreciate it. My question was, just with low frequency, just trying to make some dumb, stupid measurements. You talked about probes. Why can't I just take a B and C and maybe cut the end off of it and just, use the wires off of that? What's the effect of that?
Well, that's essentially a 1X probe. It just doesn't have a nice convenient probe tip on it. Okay. For low frequency work and for relatively low impedance circuit work, it's fine. Okay. Now let's talk about both of those, right? Because at low frequencies, the maybe 100 or 150 picofarads of capacitance that is going to be is going to be seen looking into that scope. What's the impedance looking into that coax, the end of the coax there? You got the probe capacitor, the lead capacitance, right? We're certainly talking about frequencies that are low enough where we don't have to worry about transmission line effects of a 3 or 4 foot lead piece of coax. So it's just going to look capacitive. So we're going to see essentially the 1 megohm resistance of the scope in parallel with the scope's input capacitance and the coax capacitance. So maybe 100 picofarads or more. So if you're dealing with low frequencies, the reactance of 100 picofarad capacitance might represent thousands of ohms. So who cares, right? It may not matter. But if you're looking at like a crystal mic element, which has a very high input impedance, 100 picofarads might affect its frequency response, right? It might roll it off, okay? Because it's like putting a 100 picofarad capacitor on that spot in the circuit. So you have to kind of think about, all right, if I'm looking at the circuit, how would this circuit be affected by sticking a 1 megohm resistor from this point to ground and sticking a 100 or 150 picofarad capacitor from this point to ground? And if your conclusion is that, well, the frequency is low enough that I'm not going to care, it's DC, it's audio, it's not going to care, or the impedance, I'm not dealing with circuit that has impedances in the megohms of resistance, right? Because I'm dealing with very high impedance circuits, even though I might have a 100 picofarad capacitor, it might represent a few hundred kiloohms of capacitive reactance. But if the circuit impedance that I'm looking at is a couple of megohms, then that's going to dominate that node impedance. That might affect the performance. So that's where you have to think about it, is whether or not sticking a 100 puff capacitor in that spot in the circuit is going to affect its operation. And that's where you can draw the line to say, well, I can use this little hunk of coax, or I really need a 10x probe to isolate that capacitor.
Thanks, Alan.
Yeah. Okay. All right, so let's move on a little bit. So a couple of places to use a Hamshack, a scope in a Hamshack, like a transmit signal monitor. So again, being able, so most station monitors, like I've got a sitting over here next to me is a Kenwood SM220. You can look at the modulated RF envelope. We'll look at things like flat topping, checking your AM modulation depth, looking at adjusting your PSK31 audio levels, things like that, or do like a trapezoidal monitor for amplifier linearity. We can do some analysis on coax through like a time domain reflectometer. We'll talk about that here in a minute. Also, obviously, circuit troubleshooting, equipment debug and repair, and even measuring like unknown capacitors and inductors as ways we can actually use a scope to help us do that. Even though most of us have got DMMs that can do some of that now anyway, but what fun is that when you can use a scope? So let's take a look at monitoring your TX output. Typically, you're gonna have to somehow sample your RF signal. Okay, you can build or use a resistive sampler. I've got a couple of where you're basically just tapping off of the line with a higher value resistor so that it doesn't disturb the SWR, but it also attenuates the signal a bit to go into the scope. You can use a capacitive divider. That's typically what the station monitors do, and also can minimize the loading. You can also just use a pickup coil or an antenna. You can stick an antenna on the front of the scope and have it pick up something. Or like even just a little coil of wire around as a pickup coil. That could be your scope pickoff point, and your signal is going through this way. A capacitive divider, it could be something as simple as this. I've got a coaxial line going through here. I've got a little stub going in here, and depending on how, and nothing's connected to that center coax line, but the closer I adjust that piston, the more coupling I'll get. That's kind of how this kind of coupler here works as well. And another one that's really super simple is if you got a transmatch in your shack. Well, oftentimes they've got multiple antenna ports, and there's almost always at least one that you're not using. Hook your scope up to that port, but just don't ever switch to that port. Okay, you're just using that port as essentially a pickup point. So even though you're switched to a different port to a different antenna, there's going to be enough wires hanging off of that unused port to act as an antenna to pick up enough RF to be visible on your scope. Or if you just want to poke a hole in the back of your tuner and bolt in a panel mount B and C connector with nothing at the other end, maybe except a short stub of wire like a pickup antenna, you could use that to couple RF signal into your scope. Okay. You could also build a detector or even buy a detector demodulator circuit, something similar to this, that can then follow the amplitude of your signal. So not only look at the RF envelope, but also then get another waveform that is just the RF amplitude to kind of like follow the audio or something like that. And this is typically what's done to do like a linearity measurement, where you might look at the envelope of the signal coming out of the amp, and on X or Y, and then on the other one look at the input to the amp from the RF standpoint, and you build essentially a trapezoidal view to make sure you got good linear operation of your amplifier. Okay, so this is kind of one idea and a very common way to use a scope in a shack. So monitoring the RF envelope, you might want to look for things like flat topping, look at a PSK envelope to be sure that you're not overdriving it too hard. You might want to look at AM modulation depth, and it's quite simple. It's just you look at the peak voltage of the envelope, and then the trough, and then this simple formula tells you the AM modulation depth. And this is like a single sideband signal here. We're just looking to be sure we're not clipping up at the top and that type of thing. And once you've got once you've got something coupled into your scope at a given frequency, if you know how much power you're putting out, you can get some calibrated numbers. You can kind of figure out, okay, this is 100 watts. 50 watts wouldn't be half of this, right? Because this is showing voltage, right? So 50 watts would be kind of more down and out of this area, things like that. Because remember, it's a square law type thing. But that's what the RF envelope might look like on your scope, and it's a very, very common thing to use, and it's just kind of cool to look at. So here's an example using what we call TDR, time domain reflectometry. If we inject a pulse into a transmission line, like a piece of coax, and if we don't have any load at the output of that coax, what's going to happen? We're going to get a reflection, right? That's SW. We get a high SWR. We got a 50 ohm line that's not terminated into 50 ohms. The signal gets reflected back. So by putting a pulse generator into a hunk of coax at the same point we measure with a scope, we're going to initially see that signal generator create kind of this initial step. But then when that pulse reaches the end and then reflects back, it's going to cause a secondary step to pop up here. And of course, this delta T is related to the transmission line length. And you can calculate that length, or that might be like a distance to fault. You might have a break in a line. You want to see how far down the line it is. If you know the velocity factor of your coax, you can calculate that distance to fault by measuring what that time is. You could even put in a variable load here and adjust it until the reflection goes away. And if you do that, you can figure out what the impedance is. I might have a hunk of coax that I don't know, is this 50 ohm line or is it 75 ohm line? You can kind of do that by playing with the load until the reflected pulse goes away. Then you know you've matched the line impedance. Okay, I've got some of the math in here if you actually wanted to do some of these calculations. I won't go over this right now, but it is something you can do. And I show this by doing this with a pulse generator. Okay, but if you have a digital scope, you could even replace this with a 9-volt battery and a series resistor. And you literally just hook up the 9-volt battery, have a series resistor, and just momentarily touch the input of the coax right here. And that'll inject a signal. There'll be a voltage drop across the series resistor, okay, because it looks like 50 ohms initially, and then you get the reflection back. So in a single shot, I can get this waveform because I do a stored waveform. So without even having a pulse generator, just a 9-volt battery and a 50 ohm resistor and a bare wire, just touch it there and I can get the same waveform and do these same measurements. So super cheap, easy way to do a time domain reflectometer. How about measuring capacitors and inductors? Well, we can use a nice fast edge pulse generator. You can build one out of a little logic circuit, pretty simple. And we've got a couple of circuits to actually measure capacitors and inductors. So for capacitors, we just want to measure the time constant, right? So if we have a known series resistor and we probe what's going on over here, we put that fast pulse in, we can see how long it takes that to come up. And it takes 63% of the amplitude is what you'll get after 1 RC time constant. So we know RC, we can actually just measure or calculate the capacitor. And this is kind of convenient on a scope, because if you use that vernier vertical control and adjust the amplitude of the waveform to be 8 divisions tall. So from this point to this point to be 8 divisions tall, the 63% point is when we cross the 5th division. Super simple. You measure that distance in time and you can calculate what that capacitor is. So just cool stuff, just fun stuff. Inductors, what we're going to do is just create a little tank circuit. We'll just AC couple into a tank circuit with, and you can play with the values here, but you say a known capacitor, put your own known inductor there. That creates a tank circuit that will ring at the resonant frequency. So what you do is you bang this in there, you measure this, and you measure the frequency on your scope. And then once you know that frequency, you can calculate the inductance from this formula here. So it's a little bit of math, but to me, it's fun ways of using your scope. Okay. So XY mode we talked about already. And it looks like I did have some cut and paste issues with my PowerPoint. So I think we've got a couple here that we're going to go through again. Let's just go through these again. Well, that's my fast edge pulse generator there. This is one you can build. A 74 AC 14 is a really pretty fast Schmidt trigger logic circuit. And being CMOS, it can drive relatively low impedance loads. So you parallel all these extra gates up. You can drive that 50 ohm load pretty easily. And it'll give you about a 2 nanosecond rise time. And it'll operate from anywhere from 3 to 5 volts. So that's kind of a neat thing. Okay. So that we talked about making those measurements. So anyway, there's that's kind of what we had to talk about. Just a little reminder on my YouTube channel, just youtube.com/mycall. And you've got my email address here if you've got any questions about how to do any of this stuff. But hopefully this gives you a little bit of an idea of some of the things you can do with your scope, how to use it, go pull it out, blow the dust off it, and play with it. You're not going to hurt anything. So,
thanks, Alan. That's awesome. We've had some folks, we've had a couple of folks drop off for the NAQP RIDI contest, but they were frantically texting me, telling me to make sure that I told you how much they enjoy your YouTube channel.
Oh, great. Oh, great.
Hey, any questions from the team? Andre.
Not really a question, but more of a comment. Anybody that is interested in probing line-powered equipment to check with their voltmeter at what potential the chassis is at before they put the ground lead on. Especially tube-powered equipment. They
didn't have the polarized plugs, and you could have a hot chassis. So yeah, good point.
It's seriously lets the smoke out of everything.
Yeah.
Should we not ask you why you know that?
High school lab didn't check.
Yeah.
Scope went bang. I got burned. Yeah, interesting.
Yeah.
Very
use
good.
the isolation transformers.
Yep.
Great.
Yeah.
Learn the
Hey.
hard way.
Hey, Dan, you had a question.
Comment, actually. Alan, thank you. I learned something really good today.
Great.
Looking at that calibration waveform, and I had almost exactly the waveform that you showed, where it's kind of got a rounded leading edge.
Yep. Yep.
And then you're talking about probes. I went looked at my probe, and lo and behold, little adjustment in there.
Yep.
That'll likely be that capacitor.
Exactly. It is.
I
Yep.
never knew that, so thank you.
Yep. If everybody got just one little nugget like that, that's great. But people just forget about that. And they say, why do I have this screwdriver here? I'm never taking my scope, my probe apart. I don't need that.
I can't tell you, Alan, how many times I've adjusted the little screw on my 465 scope, and I knew what I was aiming for, but I never knew what happened inside when I did it.
Yep. Yeah. So the other thing to think about too is if you get an old scope, you pick up a scope from a Hamfest, you say, oh, now I need to find probes. Take a note of what that input capacitance is, because then when you go to buy a probe, it'll tell you what capacitance range it can compensate for. Okay, so if you pick up a scope and it says it's got 15 picofarads of input capacitance, and you're going to buy a probe, and if the probe says it can compensate from 20 to 30 picofarads, you won't be able to compensate that probe on that scope. So it's important to kind of know that if you're probe shopping. John, you were muted. You were saying something.
Oh, no.
Okay.
Okay. Harry, did you have a question or comment there?
Oh, I just wanted to say thank you. I thought it was a terrific presentation. I sold instruments for over 30 years, so I never did sell tech.
Okay.
Maybe for 2 weeks, but then the ACA got terminated. I just it was one of the late things I did. I sold for Brody and HP in the past, but
okay. Yeah, well, I work for tech now, so
yeah. Yeah, I found that on LinkedIn. So anyway, I just wanted to say, this is probably one of the best sessions I've ever seen on scopes in my 30 odd years.
Oh, thank you. Thank you.
Just terrific, John. Thank you.
Thank you.
Okay. Any questions? Okay.
Just one question to go back to the probe compensation again.
Yeah.
So the capacitance that's listed on the machine on the scope.
Yeah.
And then the probe what's on the probe has to be within that range.
Yeah. So
its range has to contain that.
That's a good question. So when you're probe shopping, there will be two specs that have something to do with capacitance. One will specify the compensation range, okay? And the compensation range needs to include the actual capacitance of your scope. The other thing that you'll see on the scope spec page is the input capacitance of the probe. And what that is that's what, when you're taking that probe and touching it on a circuit, that's what your circuit is going to see. That really has nothing to do with the compensation range. So it's the compensation range that has to ensure that your scope capacitance is in that range.
Now, for the tip capacitance, what are you looking for an ideal? Does it depend on what frequencies you're looking at, or?
Yeah, well, I mean, oftentimes it's going to be what it's going to be, right? And obviously, the lower the better. Most 10x probes are in the neighborhood of 10 to 15 picofarads input capacitance. There are some higher frequency passive probes that are down, in the 3 or 4 picofarads, but they're typically pretty expensive. But most 10x probes are going to have 8, 10, 12, 15 picofarads of input capacitance. Okay, and that's just what they're going to be. So there isn't, and the higher bandwidth probes will be a little bit less. But the important thing to match it with your scope is to ensure that compensation range includes your scope input capacitance.